Welcome back, students. We ended last lecture by deriving the Maxwell distribution of molecular speeds. With this distribution, we know how fast the average gas particle is moving and the range of the distribution, so the range of the speeds that these molecules take. This was also verified experimentally. To understand chemical reactions, we next seek to know how often these gas molecules collide with each other. We'll start today by describing gas effusion, which is the formation of a beam of gas particles as they pass through an aperture, which is actually the experiment we ended on last time. So the learning goals for today are going to be able to describe collisions of gas particles with the container first in effusion or other particles to actually understand molecular collisions. And then we're going to be able to do things like calculate the collision frequency, the mean free path, so how far in space a molecule actually moves before it collides, and so forth. The rate of gas effusion is a type of collision where we determine how often gas particles collide, in a sense, with the aperture. So we can have gas particles in an oven here, and they'll go through an aperture. In order for the particle to go through that aperture, it has to, in some sense, actually encounter that in space. And then once it goes through, in the case of this experiment, it'll keep going through the aperture. So how do we describe this? The rate of collision with our aperture depends on the amount of gas particles and the size of the aperture, and also the speed that the particles are moving. Putting this information together, we can describe the rate of collisions with the aperture, dNc dt, as the number density of the particles that are moving, the area of the aperture, and then we need a term to describe the average velocity. What we're going to do is consider only the velocity in the x direction, because the aperture is on a wall of the container. So we don't need to consider velocity in all directions, just ones toward the container. So we'll talk about the velocity in the x direction. We'll multiply it by our one-dimensional velocity function in the x direction. And we're integrating with respect to velocity. What should our bounds of integration be? Well, only forward motion is actually going to go through the aperture. Reverse motion won't go through the aperture. So in that case, we're only concerned with particles that are moving in the forward direction. So we set the bounds from 0 to infinity. We plug in the one-dimensional velocity distribution function and solve the equation. So from last time, we have that the velocity distribution function, so our f of v sub x, was equal to the square root of m over 2 pi kt times e to the minus m vx squared over 2 kt. So plugging in this to the equation gives us the number density times the area. We'll put the constants out as well. So we have the square root of m over 2 pi kt. And then we're integrating now from 0 to infinity of vx e to the minus m vx squared over 2 kt dvx. And just like we've often done, we can go to the back of the book and find the solution to this integral. So the solution to this integral is as follows. The constants all stay. So we have square root of m over 2 pi kt times our number density times the area. And then the integral simply becomes kt over m. So what we can do with this is we have basically the square root of m kt, which is kt over m to the negative 1/2. We can rearrange this expression to give the number density times the area times the square root of kt over 2 pi m. The one last thing that is often done to this equation is to relate this to the average velocity. If you check your notes from the last lecture, we have that the average velocity of a gas particle was equal to the square root of 8 kt over pi m. So what we can note is that we have essentially the square root of 8 times the square root of kt over pi m. And what we have here is now the square root of 1 over 2 times the square root of kt over pi m, and 1 over the square root of 2 is 1/4 of the square root of 8. And so what we can do there is say that this is equal to the number density times the area times 1/4 of the average velocity. And sometimes it's written in this way, and sometimes it's more helpful to go back and use the actual numbers. It depends on the problem at hand, but we'll use it in this form here. We then can define the collisional flux as the collisions per time per area. Our dNc dt is already the collisions per time. So to get this collisional flux, which we'll use the letter z to denote, we can simply take dNc dt and then divide that per area. And all you have to do is take the area out of our equation above. So the collisional flux is equal to the number density times 1/4 of the average velocity. If we rewrite the number density in terms of pressure and temperature, which are often easier to gauge for a gas, we get a slightly different expression. So our number density is simply the number of particles over the volume, which is equal to n times Avogadro's number. That's the number of particles reflected in moles. And then we have the ideal gas law that gives us V is equal to nRT over P. Our n's cancel, and we can write the number density as PNA over RT, so the pressure times Avogadro's number over RT. And we could also use this as the pressure over Boltzmann's constant times the temperature. So we can substitute that back into the collisional flux, and this will give us a collisional flux of P over KT times 1/4, and we can put the average velocity back in there. So the average velocity is going to be the square root of 8 kT over pi m. Putting this all together, we end up with an expression that is the pressure over the square root of 2 pi kmt. And this again is one that we can describe the collisional flux. If we would like, we can also do this in molar quantities like we've seen before, have the pressure times Avogadro's number divided by 2 pi r times the molar mass in kilograms times the temperature. If we wanted to, we could use this above expression to determine how the pressure would change as a function of time due to effusion. And so we can do this by taking the change in pressure with respect to time, which would be equal to the time derivative of the pressure using the ideal gas law. That is n kT over V. Here we've done capital N K instead of lowercase n r. So this is simply going to be kT over V times dN dt. And we know that dN dt is the area times the collisional frequency. So that's going to be kT over V times negative ZC times the area. We have a negative sign because the pressure is decreasing as a function of time as gas molecules actually leave the container. So with this, we could go ahead and plug in our expression for ZC, and that would give us dP dt is equal to kT over V times P times Avogadro's number over the square root of 2 pi mkt. And then we'll have our negative A over here multiplied by negative A. Going through the process, we rearrange, we put this P over on this side, we bring the dt over to this side, and we can integrate this and get an expression that says the pressure is equal to the initial pressure times E raised to the, essentially, so I'll put exp here to denote this. So it's E raised to the negative AT over V times the square root of KT over 2 pi m. If we wanted to describe the change in pressure of a gas as it's leaking through an aperture. In a similar fashion to this, we can actually describe collisions between particles. In the model of effusion above, we connected the likelihood of effusion with the likelihood of collisions between the particles and the aperture. How can we describe the collisions between particles? This is going to be important for us because collisional frequency is going to be important involving chemical reactions, as we'll see in the coming chapters. The kinetic model of gases models collisions as those between hard spheres. Recall also that gas particles are mostly isolated from each other at normal temperatures and pressures. We went through this in the previous lecture. So some of the questions we're going to ask are, how frequent are molecular collisions? And we'll go ahead and go back to the slides and investigate this question. We'll start by pretending that only one gas molecule is moving and all other gas particles are stationary. To determine how many collisions are going to happen or how likely a collision is, we have to determine what particles our moving particle will actually collide with. So here in this lighter orange is our moving particle, and these red particles are all the stationary particles. We can describe a volume that our particle will move through. We can see this cylinder shown here is the volume that our particle actually carves out in space as it moves forward. It has a length and an area here that this particle will move through. The length of this particle is going to be related to the velocity of the particle. So if we want to know how many collisions this particle will make per unit time, the distance it moves is simply the velocity it's moving with times time. We've done this in physics. This is how we get from a velocity to a distance. So that is the distance of the cylinder. What's the area of this cylinder? Well, the area of this cylinder isn't simply based on our particle alone. Now, why not? Well, our particle has to collide with other particles. So the likelihood this particle will collide or what particles will collide with it doesn't just depend on the size of this particle, but it also depends on the size of what the other particles are that it's colliding with. So the radius of this cylinder here that our particle is carving out is actually the sum of the radii of our particle that's moving and also the particles that it's colliding with, since it will actually collide physically with these other particles. So the area of this sphere, of the cylinder, we call this collisional cross-section, and that's simply pi r squared, but the r is the sum of the radii of our moving particle and also its collisional partners. This setup only works if all other particles are stationary, which is obviously untrue. To account for the motion of all particles, we have to make a correction that's instead of using the average speed of our particle, we use what's known as the effective speed. That is the speed of our particle of interest relative to the others. If two particles have the exact same velocity, the effective speed would be 0 since they're moving in exactly the same direction at the exact same rate, so they're not moving relative to each other. If they had the same velocity but exactly opposite directions, the effective speed would be double the actual speed since it appears they're moving twice as fast towards each other. A full derivation of the effective speed is beyond the scope of this class and this lecture. We'll note, however, that the approach angles are equally likely, so they're not only moving, in the same line, but in any sort of direction. And if we average over all directions, the average approach angle will be 90 degrees. With this in mind, we can describe the effective speed using the Pythagorean theorem. The effective speed, which you write here as the average speed of v12, is equal to the square root of the average speed of v1 squared plus the average speed of v2 squared, the speed of our particles. These are the same, so we can go ahead and say that the average speed of v1 is the square root of 8kt over pi m1. This is squared, so we'll leave that alone. And then we have plus the square root of 8kt over pi m2 squared. And then we're taking the square root of this. So what we can do is, since everything is constant except for the mass, we end up having the square root of 8kt over pi, and then we have 1 over m1 plus 1 over m2. And we're taking the square root of that. Now, what's 1 over m1 plus 1 over m2? This is actually the reduced mass, and this is where the reduced mass that we've used plenty of times over the course of the year has come from. So if we multiply both sides of these equations by m1 and m2, right, 1 over m1 plus 1 over m2, if we multiply this by m1 and we multiply this by m2, we get m1 plus m2 over m1 times m2. And so this is simply 1 over the reduced mass. So then our average velocity becomes the square root of 8 kt over pi mu, where mu is the reduced mass. In a lot of cases, we'll be using only one type of particle where a mass of 1 and the mass of 2 is the same. In that case, the reduced mass becomes m1 over 2m1 or 1/2 m1. And we'll see that come up in the following expressions that we'll see when we go back to the slides. So with this in mind, we can go and actually describe what's happening in these collisions. So how many collisions will particle 1 make with particle 2? Well, that's actually pretty easy to describe. So particle 1 will make collisions based on how many particle 2s there are. The more particle 2s, the more likely particle 1 is to collide with the particle 2. And then how big is this cylinder, so the volume of the cylinder. And then we have to figure out the collisions per time, so we'll divide by time dt. And so what that's going to give us is the collisional frequency of particle 1 with particle 2 is the number density of particle 2 times the volume of the cylinder, right, which is the physical space that particle 1 is carving out as it moves, and then divided by dt. What we get then is n2 over the volume times the collisional cross-section sigma times the effective speed, and plugging that all in, we get n2 over v times sigma times the square root of 8 kt over pi mu. Like I mentioned on the board, what happens is we often have just one particle. So if we want to describe the collisions of one particle with itself, right, one particle with other types of itself, the mu here becomes 1/2 over m. And so that gives us this equation here where we have n1 over v times sigma the square root of 2, which comes from converting the reduced mass into the just mass of particle 1. And then sometimes this is reflected as based on pressure. So we can convert n1 over v to the pressure times Avogadro's number over RT. And then we have collisional cross-section, square root of 2, square root of 8 kt over pi m for the speed of the molecules. Now, these are collisions that one particle 1 is making with either all the particle 2s or all of the particle 1s per second. It's often interesting to know how many collisions are happening, period. We can describe the total collisional frequency that's going to be the collision between all particles of type 1 and all particles of type 2. For this, we simply need to multiply the collisional frequencies that we have here by the number density of particle 1. So if one particle 1 is making a certain number of collisions and we have a mole of them, then we need to know that. When we multiply that in, we're making a mole more collisions than if we only had one. And so we can write that capital Z12, so capital Z is the total collisional frequency, lowercase z is the just collisional frequency of one particle. We multiply the collisional frequency that one particle 1 makes all the particles 2 by the number density of particle 1, how many particle 1s there are. And this gives us an answer in collisions per second per volume. Our lowercase z's are collisions per second. We can also describe a Z11, that is the total collisional frequency for all the particles of type 1 with each other, with themselves. And to do that, we have to introduce a 1/2 term. And that's because if we grab particle A and particle B of type 1 and they collide, we've already accounted for that collision. So we don't need to go for B and then for A. So we divide by a factor of 2 to prevent double counting of these collisions, since we're talking about the same types of collisions. What is the total collisional frequency? Let's go and use an example of molecular nitrogen at room temperature and pressure. So here we can see the radius of nitrogen and also the collisional cross section of nitrogen. And using this, we can go ahead and explore how many collisions are happening per second. To calculate the total collisional frequency that nitrogen molecules will make, we can go ahead and use this equation here. So this 1 over the square root of 2 comes from the fact that we have nitrogen colliding with nitrogen. This term here comes from the concentration, the number density of nitrogen. This is the size of nitrogen, and this is the speed that the nitrogen molecules are taking. So we can go ahead and explore what's happening at room temperature and atmospheric pressure to nitrogens. The collisional cross section of nitrogen is 4.3 times 10 to the minus 19th square meters, which is 0.43 square nanometers. And we can also calculate the molar mass. The molar mass, we have to use kilograms per mole. So that's 0.028 kilograms per mole of nitrogen. You can note that this equation differs from the one on the slides in that we're using, like we've seen before, R and M rather than K and lowercase m, which reflects molar units. And it's fine to do it in either way. We can go ahead and evaluate, and this is a practice in using proper units. Everything in this equation is assuming SI units. You can make some differences if you want. But we're going to use SI units here because we don't quite have volumes, or volume is coming from areas and so forth. So what we'll get then is the total collisional frequency is equal to 1 over the square root of 2. Now, the pressure, we're using atmospheric pressure, which is 100,000 pascals, not 1 bar. Then we use Avogadro's number, 6.022 times 10 to the 23rd per mole. We're dividing by R, 8.314 joules per mole Kelvin, and then we're multiplying by the temperature, 298 Kelvin, and we're squaring that. Then we'll take our collisional cross section, 4.3 times 10 to the minus 19th square meters, and then we will have 8 times the gas constant again, 8.314 joules per mole Kelvin, times the temperature again, 298 Kelvin, over pi times the molar mass, 0.028 kilograms per mole. And this is a square root. So going through what's happened to the units, well, we've lost our per moles here, we've lost our temperatures here, and we have a pascals over joules. So a pascal is a Newton per area. So I'll just do a unit analysis here. This becomes Newton per square meter, and the joule, right, is work. So that's Newton meters. So what this term here becomes is 1 over cubic meters. It's a per volume term, which makes sense. That's what we were using it to describe. So we have a 1 over meter cubed squared term. We have square meters over here. And then in this side of the equation, what do we have? Our temperatures cancel, our per moles cancel, and we are left with joules per kilogram. Again, joules is Newton's meters, and a Newton is a kilogram meter per second squared. So we have Newton meters squared, or sorry, we have Newton meter per kilogram, which is kilogram meters squared per second squared over kilogram. So what we're left with is the square root of meters squared per second squared, or meters per second. So putting all these things together, we have 1 over cubic meters squared times meters squared times meters per second. So this gives us 1 over meters to the 6th times meter cubed over the seconds, which is 1 over meters cubed times 1 over second, which is per volume per second, the exact units that we should get. So these are the kind of things that you want to think about when solving these equations, and make sure that you're using the proper units as we go along. Now, plugging in all these numbers, that's relatively easy. This is a plug and chug problem. And what we end up getting when we do that is that Z11 is equal to 8.52 times 10 to the 34 per cubic meter per second. That's a lot of collisions. Now, we initially started with this model by assuming that collisions were not happening very often. And here we're seeing we have a whole ton of collisions of nitrogen molecules at atmospheric temperature and pressure. So we can ask one last question, which is how often are collisions with respect to distance, right? So it's the opposite of essentially of collisional frequency. It's saying how far does a particle move before it collides. And so this distance is called the mean free path, and it's exactly what I just described. How far can a particle move before it collides with something else? And so the mean free path, we use the symbol lambda to denote it, and it's simply equal to the average velocity, dt, right, the distance it moves, and then divided by how many collisions it makes. So if we have a particle that's colliding with two other types of particles, itself and something else, it would be the sum of Z11 and Z12. The dt's cancel here, and the mean free path is simply the average velocity times the sum of the collisions that our particle will make. To make things simpler, if we only have one type of particle, we can simplify this down to the average velocity divided by the only collisions that are possible, and that is Z11. We can describe this by using our definition for the collisional frequency. It's nothing more than the number density of particle 1 times the square root of 2 times the collisional cross-section of the molecule times the average velocity. So here the average velocities cancel out, and we can use the ideal gas law to relate N1 over V to the pressure, and we end up with RT over the pressure times Avogadro's number times 1 over sigma times the square root of 2. And this is the mean free path of molecules. So for nitrogen, we can go ahead and describe this just like we did before. So the mean free path for nitrogen is going to be the ideal gas constant, 8.314 joules per mole Kelvin times the temperature, 298 Kelvin, divided by the pressure, 100,000 pascals, times Avogadro's number. And then to this, we'll multiply 1 over the collisional cross section, which is 4.3 times 10 to the minus 19th square meters. And then we'll have the square root of 2. Plugging in numbers here, we get that this is equal to 6.77 times 10 to the minus 8 meters, or 67.7 nanometers. This may seem pretty small, and collisions may be appearing to be happening quite frequently, like we saw above here. Does this mean that our assumptions that gases are mostly empty space is incorrect? It does not, because gas molecules are very small. So the diameter of a nitrogen molecule is about 0.38 nanometers. So with a mean free path of 67.7 nanometers, that means on average, a nitrogen molecule moves 178 times its own diameter before it actually bumps into anything else. So the gases are mostly empty space, but the fact that they're moving so fast and actually makes many collisions happen per second, despite being mostly empty space. With either the mean free path or the collisional frequency, we can calculate the average time between collisions. So it depends on what kind of numbers we have, but this is equal to 1 over Z11, and it's also equal to the mean free path divided by the average velocity. You can get this either way. For nitrogen, this ends up being 1.43 times 10 to the minus 10 per second. And this is a pretty good estimation for collisions. So this is a pretty good estimation for collisions in general for the order of magnitude. We get about 10 to the 10 collisions per second for gases. And this is also pretty approximately true for solution-based collisions as well. So every molecule makes about 10 to the 10 collisions per second, which is about 10 billion collisions per second. This is a good kind of rule of thumb to think about things, which is helpful for a lot of just considering things. If we want to know how likely is something to happen, we were likely to get 10 billion collisions per second in the gas phase and also in solution phase.